Let's take a look at the question number 7 on your worksheet that I gave you last week, the work, energy, and power worksheet. So we did 1, 2, and 3 last week, and then we're moving into energy this week. So number 7 says a 1 kilogram balloon full of water is dropped from the top of a 100-meter tall building. Just as the balloon strikes the ground, its speed is 40 meters per second. How much heat energy is transferred to the air? Now, you might read this and say, whoa, 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 Mr. Osberg, we didn't talk anything about heat energy. And you're right, we haven't. That is another form of energy. But keeping in mind our law of conservation of energy, that the total energy before any interactions will be equal to the total energy after any interactions, we're going to be able to figure this one out. So let's draw the situation here. So we have our 1 kilogram balloon, 1.00 kilograms, and it's 100 meters above the ground. It must be a really big balloon if I'm drawing this to scale. Just as the balloon hits the ground, its speed is 40 meters per second. How much heat energy is transferred to the air? Okay, so let's look at this. Let's break this up into 2 different parts. Let's calculate the energy before and the energy after, and we can compare those, and we'll see where we go from there. So we know our potential energy, we'll call this potential energy I for initial, is mgh. So the mass was 1.00, g is 9.81, and the height is 100. So that gives us 981 joules. The kinetic energy initial is 1/2 mv, we'll call this I squared. What do we know here? So we know 1/2, the mass is 1.00. What's my initial velocity? As it's let go, as it's dropped, it's 0. So this whole thing is going to cancel out and it's going to give us 0 joules. So what's my total energy initial? Well, it's my potential energy initial plus my kinetic energy initial, which is just 981 joules because it's 981 plus 0. So 981 joules. Okay, let's do the same thing, but let's do this when the balloon hits the ground. So we'll call this potential energy final and kinetic energy final. So the potential energy final is mgh, and we could even say hi for height initial and hf for final. So the mass doesn't change, 1.00. The force of gravity doesn't change. The height now, though, when it hits the ground is 0. So this whole thing equals 0 joules. Okay, what about our kinetic energy? We know it's 1/2 mv, we'll call this f squared. So we have 1/2 times 1.00 times 40 squared. Now, when you do this, make sure you only square the 40, don't square the whole thing. When you do this, you should get 800 joules. Okay, so what's my total energy here? Well, we have my potential energy final plus my kinetic energy final equals 800 joules. Wait a second. We started with 981. We have 800 afterwards. Didn't you tell me, Mr. Osberg, that the law of conservation of energy says we should have the same amount of energy before and after? Yes, that law is still true. So why do we have a difference? Well, what happens when something falls through the air? Does it continue accelerating perfectly at 9.81 meters per second squared forever? Or does it have some surface that interacts with the air and there's some friction between the air that slows it down a little bit? Yes, that is what happens. It slows down. We've got that air resistance is what we call it. Well, what happens when two things interact with each other? In this case, a balloon and the air. Guess what happens? They heat up. Rub your two hands together. When they interact with each other and you have friction, there's some heat generated. That is a form of energy. So guess what? The difference between these is the energy that is lost to the air through the form of heat. So the heat energy is going to be 981 joules minus 800 joules gives me 181 joules. So to answer the question, how much energy is lost to heat in the air, the answer is 181 joules. So that energy is still in the system between the balloon and the air and the ground. That's still in the system, but it's now in a different form. It's in heat energy and it's in the air. So my initial and my final are going to be equal. Notice here I didn't put EF because this is not my final. If you wanted to, you could say your total energy initial is going to be equal to your total energy final, which in this case, the final energy would be your potential energy final plus your kinetic energy final plus the heat energy in the air. So in that case, my 981 over here still equals my 981 over here. We haven't just gotten rid of energy, we've just converted it from one form to another. In the first place, it was all potential energy. There was no kinetic energy. There was no additional heat in the air. Afterwards, there was no potential energy because it's on the ground. There was a lot of kinetic energy, and there was also some energy in the air. So using that law of conservation of energy, we can solve these types of problems and see where is that energy actually going. Let's look at one more example. Friction is in this question as well. Rather than between the air and the object, this is pushing something along the ground, and we're going to have friction between the ground and the object. So we've got our setup here. Let's do this question. So number one, how much work is done? So we've got an applied force. I could even write this FA to be applied force. Well, how much work is done? We know that work is the dot product of force and displacement. Our force applied here and our displacement are in the same direction, so we don't have to do the cosine of anything here. So we could say the force is going to be 7 times the cosine of, there is an angle of 0 between those, so that cosine of 0 is actually 1, so 7 times 1 is going to be 7, times the displacement, which was 200 meters. So 7 times 200 is 1,400, and this is joules. So there's my answer for number 1. What is its final speed? Okay. How are we going to do that? So how do we know that it has a speed? Well, if you look at this, the sum of the forces here is not 0, so we know it's actually going to be accelerating. So if we do number 2 here, we know that the net force in the x direction is going to be my applied force minus my force of friction, which is also going to equal what? Mass times acceleration. So we have 7 subtract 5 equals 23 times a. 2 equals 23a. A equals 2 divided by 23, which is what? Oh, I made a mistake here. This is 23 grams. So remember, we need to convert grams into kilograms. That's our base unit for mass. So 23 grams divided by 1,000 is 0.0023. No, sorry, I'm off by a decimal. 0.023 kilograms. So we have 0.023a, 0.023a, and when we do 2 divided by 0.023, we get 87 meters per second squared. Okay, so now we know how fast it's accelerating. What is its final speed here? We could do Vf squared equals Vi squared plus 2AD. We're going to use that kinematic equation. So VF equals the square root of all of that. VI squared plus 2AD. So 0 squared plus 2 times the acceleration we just found times the distance, which was 200, gives me 187 meters per second. Wow. That's pretty quick. So there's my answer for number 2. It's traveling 187 meters per second. Number 3, what is the final kinetic energy? So you can see now that we know how fast it's going, we can calculate kinetic energy. So we'll call this KEF equals 1/2 mvf squared. So 1/2 times the mass of 0.023 times 187 squared. When I plug that in, I get about 400 joules. All right, number 4, how much energy is lost to friction? Okay, where is that question coming from? Well, let's take a look. At the start, how much work is done? 1,400 joules, right? Or sorry, not at the start, but how much work is done overall is 1,400 joules. That is also my potential energy at the start. What was my kinetic energy at the start? Oh, kinetic energy at the start. Well, it's not moving, so it's 0, right? So what is my net energy initially? 1,400, right? This is asking how much energy is lost to friction. Well, what's my final energy? Right? So what is my energy at the end? Well, we have potential energy plus kinetic energy plus, why did I put it a plus? Well, we know, wait a sec, my potential energy is 0. My kinetic energy is 400. And what do we know about the total energy final and the total energy initial? They should be equal to each other. So we have 1,400. 1,400 does not equal 400 unless you're doing your math wrong. So we have something else here. Well, what is that? That's the energy lost to friction, right? So let's just call this EF for friction. Well, that's an italicized F. So EF is going to be 1,400 minus 400 equals 1,000 joules. Does that make sense? Yeah. As you're pushing something, it's not going to accelerate perfectly forever. And it's going to interact with the surface that it's on. They're going to rub together, create friction, create heat, and we're going to lose, quote unquote, lose some energy due to that. And that lost energy here is 1,000 joules.